So what does this mean? Okay, this means that metals give all of their valence electrons away. Okay, when they do so, the reason that they give all of them away is that those are the electrons in the highest energy level, and there's not very many. When they give those away, the highest energy level is now empty. So the next highest energy level is now the highest energy level. And that one is already filled up. So they have full s and p orbitals. Nonmetals take valence electrons to fill up their s and p orbitals. Okay, so what does that look like? Okay, so let's say we have sodium, which has 1 valence electron, and a chlorine atom, which has 7 valence electrons. Okay, so sodium is, remember we said that it was Na3S1. That's the valence electron. Chlorine is Na3S2, 3p5. Okay, so chlorine has, here's 2 and here's 5 or 7. So this orbital is not completely full. It can hold up to 6. So what happens here is we're going to see the valence electron from sodium is going to get transferred over here and given to the chlorine atom. So now sodium atom isn't 3s1 anymore. Just looks like neon. And the chlorine atom becomes 3p6. 3s2 neon 3s2 3p6. That's the valence that's the electron configuration for argon. So now they both have the exact same electron configuration as one of the noble gases. Now they don't turn into the noble gases because only the changes in the nucleus, changes in the number of protons, could change an atom of one element into an atom of a completely different element. Well, what's changed? Okay, sodium is atomic number 11. So that means it has 11 protons and 11 electrons, right? Chlorine is atomic number 17, which means it has 17 protons and 17 electrons. Now, if we just said that we took one electron away from chlorine, from sodium, and we gave it to the chlorine. Now look what happened. The number of protons and the number of electrons are not the same anymore. So before this was plus 11, now it's negative 10. If we add those two together, we get a positive 1. There's an extra positive charge left over. Over here, this was positive 17, and now it's negative 18. So it has 17 positive charges and 18 negative charges, which means it becomes negative 1. So what happens when the metals give away their electrons? They gain what we call a positive charge, because they lose some negative charge, and these become what we call a cation. Nonmetals, when they take the electrons, now they take an extra negative charge, and they become negatively charged particles that are called anions. Okay, well, what does it mean now that we have a positively charged cation, sodium, and a negatively charged anion chlorine. Well, these are opposite charges, which means that they are strongly attracted to each other. Okay, and the positive negative attraction has a special name. It's called because it's for about electricity. Static, because we're not talking about flowing electrical current. We're talking about charges that are basically not moving. Electrostatic attraction. Okay, and this creates what is called an ionic bond. An ionic bond is when a positive cation and a negative anion are attracted to each other. It's very, very strong. It's just as strong. The electrostatic attraction between a positive and negative charge is just as strong as the force of gravity. From the Earth to the Moon, or from the Sun to the Earth. It's like gravity. The closer they are, the stronger they feel attraction. So can we pull them back apart again? Yeah, we can. And it's going to be very hard at first, but the farther we can get them apart, then the less they're attracted to each other. Just like an airplane can fly high enough out in the Earth's atmosphere that it's not quite as attracted. And spaceships can get far enough away from the Earth that they leave the atmosphere and they leave the Earth's gravitational pull completely. So they're not attracted to the Earth anymore. The Earth doesn't attract them. Alright, so that's what we call the ionic bond. Alright, so we see here that there's these charges here, positive and negative charges. Okay, these are what we call oxidation numbers. Okay, every element has an oxidation number. This is a number that shows the charge, positive or negative, and the number of electrons gave away or took. Now, sodium had one valence electron. Remember, all of the alkali metals had one valence electron. So that means that all of the alkali metals will follow the same pattern as sodium, give away one valence electron, so one particle of negative charge, and end up with one extra proton in their nucleus compared to the number of electrons left over. Chlorine is a member of the halogen family. They all have 7 valence electrons. They're all going to take one extra unit, one extra electron of negative charge. So they're all going to end up with a -1 oxidation number. So we're going to go back to our periodic tables. And now, instead of writing down the valence electrons, we're going to label the periodic table up with the oxidation states, or the oxidation numbers. Okay, so I'm going to write these on the top of the column. So we said that the alkali metals are all +1. Now hydrogen can be positive or -1. Hydrogen is 1 electron. It can act like a metal, and it can give away the 1 valence electron. That leaves it with just a proton, which gives it a +1 charge. It can also act like a nonmetal and take 1 extra electron from something, so that it looks like helium, and that will give it a -1 oxidation state. Okay, the alkali earth metals have 2 valence electrons. If they give them away, then they'll have 2 extra protons in the nucleus, so they'll have a +2 charge. Okay, just like the number of valence electrons varies, oxidation number varies for this whole family. Okay, we will come back to talk about, well, they do bond and they do give away their electrons. Well, we'll talk about how do you know the oxidation number for all the different elements in the transition metals. Okay, the boron family. Remember, this is where we start getting the split. These families are not all metals or all nonmetals, except for halogens and noble gases. So boron is a metalloid, but boron is on the nonmetal side of the stair-step line. So it tends to take electrons, right, or share electrons, but it's a little more complicated. We actually find boron does something different other than giving and taking electrons. We'll talk about that in a minute. Okay, the carbon family are plus or minus 4. Carbon and silicon, the nonmetals, would become minus 4, and germanium and tin and lead, because those are all metals, will become positive 4. Because remember, metals are going to give away the electrons, nonmetals are going to take the electrons. So metals always make positive oxidation numbers. Okay, you can make a note for yourself somewhere. Always positive, and nonmetals are always negative. Alright, so nitrogen, now we have more nonmetals than we have metals. So these tend to take, they have 5, they tend to take 3 more to fill up their S&P orbitals, giving them a negative 3. Oxygen has 6, so they tend to take 2 more to fill up their S&P orbitals. And the halogen family, like chlorine, remember we said just needs 1 more. The oxidation state over here is 0. Okay, these don't bond. Okay, we do find a few compounds between krypton and xenon, but they don't make ions. They do something a little different.